Hi, my name is Arasu, and in the previous video we saw how Greek astronomers built trigonometry using chords of a circle. If you knew the central angle, you could find the length of the chord connecting 2 points on the circle. But around 300 years later, in India, a mathematician named Aryabhata made a subtle but profound change. Instead of using the full chord, he used just half of it. If you draw a chord in a circle and draw a perpendicular line from the center, you split the chord into two equal halves. You get something like this. Each half forms a right triangle with the red line. And the vertical height of this triangle, so this length here, is what Aryabhata called ja, which we now call sine. This small geometric shift made the entire system of trigonometry simpler. The Greeks measured the full chord between 2 points on a circle. Aryabhata measured the height of a point above the horizontal line here. And with that change, trigonometry stopped being purely geometric and started becoming numerical. But before we can understand how Aryabhata constructed his sine table, we need to understand the units astronomers used to measure angles. Astronomers didn't measure angles in degrees the way we usually think of them today. Instead, they divided each angle into 60 smaller units called arc minutes. So a full circle contains 360 degrees, so 360 times 60 equals 21,600 arc minutes. Aryabhata then let the circumference of his circle equal 21,600. This means that the angle between two radii, this theta here, is equal to the arc length. And if we divide the circumference by 2 pi, we get the radius as roughly 3,438. So Aryabhata set the radius of his circle to 3438 units. But why is this useful? Because with this choice of radius, small arcs behave almost like straight lines. For very small angles, the arc length and the vertical height of the point above the diameter are nearly the same. So, for example, if the arc between two radii is 225 arc minutes, the height of the point from the horizontal diameter, in this case h, will be very close to the arc length, which we know is 225 degrees. So we can say that the height will be equal to the arc length if theta is quite small. This observation gives Aryabhata the first entry into his sine table. But his real genius was discovering how to compute the rest. Aryabhata did not compute height or sine values for every possible angle. Instead, he divided the quarter circle, or 90 degrees, into 24 equal steps. Each step is 3.75 degrees, which is 225 arc minutes. So Aryabhata's table contained 24 numbers, one for each of these angles between 0 and 90 degrees. But these numbers weren't abstract trigonometric functions. Each number simply represented a height. Imagine a point moving along the circle. From that point, drop a vertical line down to the horizontal diameter. So, like this. The length of this vertical line is the height of the point above the diameter. Aryabhata recorded that height for each angle or each step. So as we move along the circle in equal angular steps, the point rises higher and higher, and the height increases. Only much later would mathematicians recognize that this height is exactly what we now call r sine theta, or simply sine of the angle. But the increase does not happen at a constant rate. At the beginning of the circle, you can see that the height increases rapidly. The difference between 1 and 2 is almost double. But as we move higher toward the top of the circle, the curve starts to flatten, and the height increases more slowly. So as you can see, the difference between 4 and 5 is almost nothing. Aryabhata noticed this pattern, and instead of computing each height from scratch, he looked at the differences between successive values. Suppose we write down the height for each step, or draw in this case. Then we compute the difference between each pair of consecutive values. So these blue lines here. At first, those differences are quite large. But as we move around the circle or the point gets higher and higher, the differences start to decrease. In other words, the amount by which sine increases slowly decreases as we approach the top of the circle. Aryabhata realized that these differences themselves follow a predictable pattern. Each difference is slightly smaller than the one before it, as you can see, and the amount by which it decreases is proportional to the current height. This leads to a recursive rule. To find the next difference, you take the previous difference and subtract a small fraction of the current height. Then you add this new difference to the current height to obtain the next height. So the table can be built step by step. Each value produces the next. Each difference produces the next difference. Instead of solving a new geometric problem every time, Aryabhata turned the circle into a numerical process. In modern notation, historians reconstruct Aryabhata's rule roughly like this. Let hn be the value of the height at any step n. Let dn be the difference between two successive heights. The next height value is obtained by adding the current height value and the difference. So, hn plus 1, the next height, is equal to current height plus the difference. But the difference itself slowly decreases according to dn plus 1 is equal to dn minus hn divided by 225. Or next difference is given by current difference minus the current height divided by 225. The number 225 appears because each step of the table corresponds to 225 arc minutes. So the change in the differences is tied directly to the angular step size Aryabhata chose. Starting from the first height of about 225, which is given by the angle of 225 arc minutes, and we're approximating the height to the arc length, the first difference is also 225, or d1 is equal to h1 minus h0. And we take h0 to be the flat line or the diameter, which has a height of 0. Starting from the first height of about 225 and the first difference of also about 225, this rule can generate the entire table. Step by step, the algorithm walks along the curve of the circle. What Aryabhata created was more than just a table. He created an algorithm. Greek trigonometry relied heavily on geometric constructions, inscribed polygons, and theorems like Ptolemy's theorem. Aryabhata replaced that geometric machinery with a numerical procedure. Instead of constructing shapes, you could simply compute. In a sense, Aryabhata had discovered a method that quietly encodes the curvature of the circle. The height or sine values follow the curve of the circle, and the recursive rule captures how that curve bends. He did this without calculus, without algebra. Just geometry, insight, and arithmetic. With Aryabhata's sine table, trigonometry had taken a major step forward. The Greeks had discovered how to measure angles using chords. Aryabhata transformed that idea into a system of half chords, which behave naturally inside right triangles. Over time, the Sanskrit word jya became jiba, which was later translated into Arabic. When Arabic texts were translated into Latin, that word became sinus, meaning fold or curve. From there, we get the modern word sine. In part 3, we'll see how this idea eventually evolved into the trigonometry we use today, the system of sine, cosine, and tangent that appears in every mathematics classroom. But its origins lie in a simple geometric idea: the height of a point on a circle. That's it for this video. Thanks for watching, and I'll catch you in the next one.